Hello and good morning. Recently, we have published one paper in Geophysical Journal International. In this paper, we have defined the nature and geometry of the main Himalayan thrust beneath Kumaun Garhwal Himalaya region based on rock lithology, which is derived using integration of seismic imaging with other geological and geophysical information. As you know, Indian plate underthrust beneath the Himalaya and Tibet along the main Himalayan thrust MST. There, while not only MST is useful to study the upliftment and growth of the Himalayan or orogeny, but also to understand the earthquake occurrence in the Himalaya. Various studies shows variation in the MST along the Himalayan arc using geophysical and geological methods. In geophysical methods, especially in seismology, the MST is defined based on the occurrence of or the observation of low velocity layer in the middle crust. In the magnetotelluric, the MST is defined based on the mid-crustal high conductive layer. However, it is a question whether MST is at the top of this anomalous layer of either low velocity or high conductivity, or at the base of this anomalous layer. In this is the general Himalayan map, where you can see the location of the great to large earthquakes in the Himalaya. This is a zone of central seismic gap where no large to great earthquake occurred in last 2 centuries, and a proposed site for the future great earthquakes. Our study area, Kumaun Garhwal Himalaya, falls in this area, which in the past has experienced great earthquake in 1803 and 1505. Therefore, to understand the seismic hazard, which is largely dependent on the nature and geometry of the MST, we try to investigate the MST in this area using seismic tomography with the help of a network of 41 broadband seismic stations. We plot our results along a cross section which crosses all major subdivision of the Himalaya along this line and all major faults in this area. This is the VP image and VP by VS image. If you see in the mid crust, the velocity is low, normal to low, whereas in the VP by VS image, the mid crust is of high VP by VS. These anomalous zones are very well correlated with the 1D shear wave velocity models as derived by the receiver function analysis. Now the question comes, what could be the reason for this low velocity and high VP by VS, whether it is partial mat, aqueous fluid, or both, or something else? Therefore, to constrain these further, we make use of the available information from the magnetotelluric study in this area, where the 2D electrical resistivity image shows in the mid crust of high conductance, whereas the LG attenuation study shows that north of the MCT, the Q value is low. It means the high attenuation, whereas to the south of MCT, the Q value is high with low attenuation. So we combine all these available information, and in the MCT and to the north of MCT, heat flow is high, conductance is high, attenuation is high. The seismicity is mostly confined up to 16 kilometers. So with the information of brittle-ductile transition zone at up to 16 to 18 kilometer depth, and a porous layer can be below the brittle-ductile zone. So with the possible presence of porous layer, we believe that the low VP and high VP by VS ratio in this area could be due to presence of the partial mat with low mat friction, whereas in this area with the low attenuation and moderate conductance, we believe that normal VP and high VP by VS ratio could be due to saline-rich aqueous pore fluid. So we believe that as the Indian plate with felsic upper crust of high radioactive production, high heat production, under thrust, metamorphic dehydration reaction takes place and induce water saturated partial melting at low temperature in this area. So therefore partial melt along with aqueous fluid present in this area, and which get separated in this area. Mostly partial melt exists, whereas due to positive buoyancy, aqueous fluid takes place in this area. So with the inference of the possible presence of the fluids in the mid-crustal level, we believe that the MST is at the base of this anomalous layer, which is of flat ramp flat geometry, where the ramp is between 16 to 19 kilometer depth and a width of roughly around 10 kilometer. So the dip of this ramp is around 17 degree. So to further go to relate it with the occurrence of the earthquake, we make use of the GPS measurements available in this area. GPS study shows that the upper flat portion is strongly coupled, so it is of locked rheology, whereas the ramp is partially locked. So the MST is considered to be of the locked rheology at the temperature less than 350 degree, whereas of the crypt rheology at a temperature of more than 450 degrees centigrade. So we combine this information with the argon-argon thermochronology as well as inverted thermal gradient, and find that the locked to crypt rheology transition is of a width of around 10 kilometer, which very well correlate with the inferred width of the ramp from this study. So when we put all together all the information of MST geometry, locked to crypt transition zone, as well as brittle-ductile transition, we infer that there is a anomalous zone at a depth of 16 to 18 kilometer at the below the surface trace of the Munsiary Thrust, that is south of the MCT zone, which could be a zone for future large earthquake in this area. So, but this required further investigation